Welcome to podcast 17 of the MotorDoc podcast. So we have coming up on January 22nd at 9 a.m. Eastern, we have the Mobius Wow week of webinars coming up. And I guess I'm the opening webinar. So we will be talking about the direct relationship between electrical signature analysis, vibration, energy, and emissions. Basically the stuff you've seen me talking about, both in the electrical signature analysis and vibration, and I believe I also included motion amplification. We're going to include that in here. Not just the stuff that I showed in the podcast, but I rented a couple of dynamometers for this particular part. It will not be the conclusion. The conclusion of the study will be presented during the August Vibration Institute meeting. That's going to be a lot of field testing, and primarily it'll be vibration and electrical signature analysis, and where I can will include the motion amplification stuff. But the nice thing too is this was also a way to directly tie and verify the accuracy of the vibration instrument we were using and the accuracy of the motion amplification when it performed properly, right? So that's there. That is then, I will include a link here. Because it for whatever reason it's just difficult to get to because it's a C-vent and you have to go and find it on Mobius in order to get there. So I will include on both the podcast page on MotorDocAI.io and also on the YouTube channel the links, and then when I post it on LinkedIn, of course. So that's the main thing there. So let's go ahead and we are going to get on today's topic. And today's topic is going to have to do with harmonics. And we are going to talk in particular about the impact of before and after. And this in case we're going to skip power harmonics, we're going to skip neutral harmonics, we're going to go straight to ground. So let's start with what happens on ground. And yes, that is 31 amps. So we're going to talk about this. Now what's kind of neat on single phase systems is the formula we're going to use is, power in watts equals voltage times current times cosine of the angle phi, which is a range between 0 to 1. That is your power factor, right? So phase angle, when I talk about power factor, and I have kVA or VA, kilowatts or watts, and I have kVAR, there's an angle present. That angle is phi, and the cosine of that angle gives me the number that you usually see. So when they say I need a power factor of say 0.9 or something like that, that would be the result of the cosine of that angle, which is going to be somewhere between 0 and 90, right? So it's going to be up here. Now 90, of course, you never want to achieve. That'll be completely out of phase. But in any case, we have that first. So we're going to use this. Now we know that my fundamental, this is actually not 60 hertz. This is actually, because the crossovers here, if this had come up, hit the peak and down again, that would be 60 hertz. But because I have such high triplet harmonics, or third harmonic content, it actually shows on my meter as 180 hertz. So this fundamental here is not 60 hertz. That's actually my third harmonic. So the voltage present, because we need to know voltage, when we did the test, was 62 volts. Okay, between the primary, my 60 hertz, but it also showed up as tripling. And then out here, when I hit ninth harmonic, which is that third harmonic, so that would be fundamental and third. And for the ninth harmonic, that turned out to be 12 volts. Okay, so this remained consistent before and after the correction. We went in and we applied Onyx Energy's OES 11s on the ground plane, across and parallel. That's a shunt inductor type filter. So that went on there. I was the one who introduced it to ground some time ago, because I've used that type of device on ground to clean up noise. That, of course, is a lot of noise. So in addition to what we're going to cover, which is the actual losses associated and emissions, all these crossovers are going to affect all of the other systems. And this is a cryptocurrency site, so all of this, I mean, this is so bad that the neutral harmonics are pure. I mean, pure 180 hertz. So those became interesting, because when we started fixing all that stuff, we got a reduction in total energy of somewhere around 6% so far. And that was just through basic applications at the transformer and then ground. It was difficult to do the actual panels. So we're going to have another site that we're doing, and that we're expecting to be much, much higher. So in any case, we take a look at this, and we want to clean this stuff up. We got 31 amps peak right there, which is going to be roughly 24 amps, right? So just because of the noise and everything else. In reality, it was telling me the third harmonic is 14 amps because of everything else. So let's take a look at that. So our values beyond that first one are 14.9 amps for third harmonic. Okay, so that's third. And then ninth harmonic is 1.142 amps. Okay, so we're going to take this and we're going to apply it to this. Now, just because I had to do these separately, I don't know the exact angle. So we're going to get lazy. We're going to leave this out. Now, if this was three-phase, I would add a square root of 3. Whoops. Square root of 3 times at the front of this. But we're not doing three-phase. We're doing single-phase, so we just do that. So when I come in here, it's going to be, we're gonna come back and we're gonna hit the fundamental too, but we're gonna say, okay, losses equal 14.9 times 62 plus 1.142 times 12, and that's going to give me volts plus 1.142 times 12 volts. That is a total of 937.5 watts, or just under a kilowatt. Okay, so that's our first bit. Now, because this is ground, if this was on neutral, yeah, I'd still probably pick it up as part of the losses due to unbalance, and then as a result you have the current. There's a different setup for that, so we're just going to focus on that. So our direct harmonic losses are just about a kilowatt. So now let's take a look and say, okay, what are our total losses? Now this is the losses on the branch. This does not include resonance losses and all of the other losses that occur in the transformer, as well as other I2R losses in the facility, even in the conductor, right? So actually in the conductor, this is where we are, conductor and part of the ground. There are other factors that come into play as far as total losses go. So this is just a quick idea of what the losses are, but not a complete value. So we're going to add on to that 24 amps times 62 that equals, or that value is going to be $14.88. Okay, then we add on our 937.5, which gives us a total of, we'll just round it up to 26, okay, watts, or 2.426 kilowatts. So we have that. So now if we do convert that over, so that would be, and we say, let's get rid of that, and we're going to say it's going to be 8,760 hours. So times 8760, and that's kilowatts, so 2.4. So that will be 2.426, oops, divided by 1,000, takes just as long, times 8760, which is year round. That is a total of 21,252 kilowatt hours. So if we then say that say 10 cents a kilowatt hour, in some areas it's higher. In this case it's actually a little bit lower, so that comes out to 2,125 per year dollars. Okay, so we have that's our primary. Now we take this and we say that's 21.3 megawatt hours times 0.709 metric tons of CO2 per megawatt hour. So we'll divide this by 1,000 again, times 0.709. This would be our excess CO2. That would be 15.1 metric tons of CO2 per year. Okay. Oh, that should be down here, but that's all right. Close enough. We know what it is. So about 15 tons. Now, let's see what happens when we applied the corrections. So this is at 180 hertz, looks real ugly. We put the we put the ground filter in place. This is now 60 hertz. Yeah, quite dramatic, isn't it? So this now fundamentals at 60 hertz. This here is now our third harmonic, and then our ninth harmonic, there's a little fifth and seventh, but we're more worried about our ninth harmonic. So let's go ahead and see where we are. So now our fundamental is going to be at 20.4 amps. That's the fundamental. Third harmonic is 180. It's a 1.1 or 813, 1.813 amps. And then our ninth is down there, 0.279. 0.279 amps, 9. Okay, so our triplets are that. So if we come back up here and we do the same thing, okay, and we're going to do this first. We're going to look at the third harmonic part first. So then we'll follow everything else. 1.813 times 62, no change in voltage. Now this is literally within 2 hours. So we took the measurements before shutting down any equipment, shut down the equipment, put the harmonic, well actually there's a number of them we put in, but we put in the ones across ground and then restarted, so about 2:30 to 4:30, and then started back up, and then we took the readings about 5-ish after everything restarted and came up to speed. Cryptocurrency site, we had to wait for all the miners to get started again, which are immediately loaded. That was just amazing. So in any case, 0.279 times 12 volts, and that gives me a total .813 times 62 equals plus 279 times 12. Okay, so 112 and 3 gives me 115 or 116 watts. We're just going to round it down to that, or round it to that, watts. Big difference. Okay, so this is where primarily we're knocking out that third harmonics, or that third harmonic. Now we're going to take that and let's add this 20.4 times 62. So what happened to our peak? Well, it's coming down as well because we don't have all that harmonic there, so less loading from the triple and harmonic. So it had a direct impact on peak current, going from 31 down to 20, 20.4 to be exact. So about 20, about a 6 amp drop from that load, basically. So that ends up being 20.4 times 62, and again I'm not including the so that's 1265 rounded up. So I'm not including the I'm including this now as the line frequency. So that drops us down about close to right over 200 watts as well. So between 200 and the other, we're going to be about half. So if I add this to it, so basically putting that on and smoothing it out, but still having the potential voltage, that's where that problem lies. So the voltage has to be balanced out. That means some work has to be done on the grounding system. It identifies a defective grounding system, basically. Should not have that much voltage present. That means safety devices aren't working right and everything else. It was even worse before with the harmonic content, but it's still present. So say 1265 plus 116, I know it'd be faster to just do it in my head, comes out to be about 1381. Watts, or 1.381 kilowatts. Okay, so if we look up here and we have 2.4 to 1.3, we've dropped by more than a kilowatt per year. So that that means that we have now dropped that to well, let's say we need to multiply by 8760, right? Number of hours per year, which gives us 1381 times 8760 gives, whoa, that's not right. 1.381 kilowatts times 8760. That's slightly different than the other number, right? So 12,098 kilowatt hours per year. Okay, so that comes out to be at 10 cents per kilowatt hour. That comes out to be 1,210. So about half the cost. Okay, so about half the cost there. Now if we go 12.1 megawatt hours, divide that by 1,000 times 0.709, means this would be, this isn't the potential, this would be the potential difference. I'm just doing this to show the difference between the two. Let's see, that would be 12.1 times 0.709. That's a potential reduction of 8.6 tons of CO2 per year versus 15.1, so almost half. So reduction by almost half just by installing one filter. Again, doing some of the other corrections is going to have dropped that even more. So when you start looking at this and you start looking at some of the other impacts, now next week we're going to cover power harmonics and we're going to cover neutral harmonics, in which we're dealing with the actual voltages associated with those points in power supply. So that'll be interesting. And we'll be able to show you some of the other potential. Now again, conservative values, that's important. It is a conservative value at this point, meaning that I would expect the reduction to be much, much higher. And with that, I would like to thank you very much, and we will see you next week, and then we will see you hopefully watching the presentation on the 22nd. Also, make sure to take a look at all the other presentations on the WOW. There are quite a few great ones. I am going to be involved in a bunch of meetings that week online and assembling product and doing software stuff. So I'm going to be watching a lot of those in the background. So thank you very much and have a great day. And by the way, enjoy the weather. It's like -10 outside.